Thank you, thank you. So today I would like to talk about how not to use Akka for a change. I picked 8 anti-patterns. I have a lot more up my sleeve, but I did a healthy mix, and I hope you will like what you're going to see today. So let's get started with this. The reason why I'm giving this talk today is because Akka is a toolkit as opposed to a framework. So it doesn't frame your work, it's a tool, you can use it any way you please, and you can also hurt yourself. Who knew actors could bite? This is what I sort of noticed and saw in quite a few projects over the past few years, and I thought it would be useful to point out some of the ways that are the most common to not to use Akka in production or at all. A few words about myself. My name is Manuel Bernhardt. I work as an independent consultant. I like scuba diving. That's me there. It's not. I live in Vienna, in Austria. This is not Vienna, Austria. This is not the Blue Danube. I'd love it to, but no. What I'm doing most of the time is helping teams getting started using reactive systems. I also work as a trainer, so I'm a Lightband partner for training such as Fast Track to Scala, Fast Track to Akka, Advanced Akka. If you need any help with reactive systems or if you need to have your team trained, just ping me on these technologies and we'll talk. I also wrote a book called Reactive Web Applications. It's covering Play, Akka, and reactive streams. The examples in the book are in Scala. And if you plan on getting started with the stack, it's the book I would like to have had for myself when I started this and didn't have. So this is sort of what I wrote as a vengeance afterwards, sort of when I learned how it actually worked together. Okay, so without further ado, let's get started and talk about how not to use Akka. Our first anti-pattern, so you will see this throughout the talk. I will start with a quote and then I will have the anti-pattern. And you will see that the quotes are not getting any lighter, they're getting darker and darker as we proceed. That's on purpose. So just a question before we get started here. Who is using Akka? Oh, wow. In production as well? Wow, okay, man, you are, just fasten your seatbelt. I mean, and I hope I don't hear too many people scream. The first anti-pattern. If you want to make enemies, try to change something. That's by Woodrow Wilson, the 28th President of the United States. Our first anti-pattern is global mutable state. So we all know it's okay for an actor to have mutable state. That's why we use actors, because an actor gives us this illusion that everything is okay. Inside of the actor, we can use mutable things. Everything is going to come in one message at a time. We're not going to have any concurrency issues and overlapping things, except that there is one thing we have to make sure of, is that the actor actually retains total control over its state and is the only one to see the state. The moment we start leaking the state to the outside, we're in trouble. So how could this happen that we're leaking state to the outside? Well, we could send a message out that contains a reference to our mutable map or whatever we have as mutable state, or we could use, we could do an asynchronous call, like a call to a web service inside of an actor, and inside of the result of that call, we could close our mutable state. Then again, we're back in a bad place where we have concurrency issues. We could also, I've seen this a few times, is people passing mutable state in the constructor of an actor. You know how you can construct an actor, you have a constructor, you have the props, and then what I've seen is like let's use this mutable map as a way of configuring my actors and sharing it amongst actors. That's a no-go as well, because even if it may work if you're using maybe a concurrent data structure, the moment you go on a cluster, you're lost. It's game over. So don't do that. Don't use mutable state in the constructor either. But I'm telling you this, and you may believe it to me. I'm just going to tell a bit more about why this is really bad. And for this, I'm going to quickly talk about what actually makes Akka tick and how is Akka working. So here I have my thread pool, my threads. These are the threads. I can draw beautifully. These are threads. These are the actors, the round things. These are messages, the square things. They're supposed to be envelopes, but I just drew squares here. And then this magic thing here, this diamond-shaped thing, is a dispatcher. And the dispatcher is what makes Akka tick. The dispatcher is the thing that's going to take a thread, pass it on to an actor for it to be able to process a few messages. The default amount of messages, the default batch size is called is 5. Here it's only 2 because I didn't have enough space. But let's say this is how it works. You have a thread, the dispatcher gives it to an actor, the actor now can process 2 messages, and then it can move on and pass that same thread on to another actor for it to process 2 messages. What could also happen is that I then have another thread passed to my first actor for it to process further messages. Which means that at no point in time should you, if you use Akka, make any assumptions as to what thread is running your actor, because they change. It's not you who control it, it's Akka, that, Akka is trying to optimize this. By default, this guy here, this thread pool, is a fork join thread pool, the one introduced in Java 7. And it's quite optimal, especially in most cases, you will have an actor system with heterogeneous actors. They're not going to all want to process the same, have the same workload at all times. So in this case, this model is actually paying off because it makes optimal use of the CPU, of the resources. If you had the idea, for example, to use, for whatever reason, a, how are these things called again? Thread local in an actor. That's not a good idea because here you don't have one thread, you have many threads. You could say I want to use a pin dispatcher, which is one that just pins one thread to one actor. In some cases that makes sense, in most cases it doesn't. So just be aware of how Akka works and how it ticks and the fact that you don't control how it works. So in order for the illusion to work, you need to make sure that you're maintaining this here. So a few rules, how not to shoot yourself in the foot here. Use immutable messages. In Scala, that's easy. We just use a case class with immutable data structures, and then we're fine. If we want to do configuration changes, what I mentioned with the constructor having configuration values, we just send it messages. We broadcast messages to all the actors that need a configuration update. If we want to know what the state of an actor is, we just query for it. We can use the ask pattern for this if we come from the outside, but we don't try to peek at what's inside and grab the state. We just really gently ask the actor to reveal what the state is. In case of asynchronous calls, I will come back to this later. Always use the pipe pattern, which is a way of bridging futures, asynchronous calls, and actors and message passing semantics. That was our first anti-pattern. Let's go crank it up a notch. The 2 enemies of human happiness are pain and boredom. That's Arthur Schopenhauer, very optimistic philosopher, I think. The second anti-pattern I want to talk about are flat actor hierarchies, because let's be honest, what could be more boring than a flat actor hierarchy? A flat hierarchy doesn't make sense at all. It's an oxymoron. It's a flat hierarchy. So this is a classic painting by Magritte in 28, Ceci n'est pas une hiérarchie. So here you have the root guardian, here you have the user guardian, and here you have the actors of the application. So here we have 3 top-level actors. And if that's your hierarchy, you're in for trouble. I mean, what that means, if this is your application, if this is how you're designing your actor system, you're missing the point of Akka. Akka was designed, and one of the main things of Akka, one of the main points for using Akka is not only to parallelize things or have concurrent applications, also have a system that's self-healing, that's reactive, that's failure tolerant, and for this you need hierarchy, because in Akka, it's through the hierarchy that we're handling failures. We have an actor supervised by another actor, and the supervising actor is going to be the one that decides what's going on, what's going to happen if there is a crash, if there is a failure. If you don't have a hierarchy, you don't have supervision. You do actually have some form of default supervision. It's just going to restart things. But you know, not all applications, not all actors are going to behave very well if all they do is restart every few milliseconds. That's not gonna fly. I mean, by default, that's what happens. The user guardian just keeps on restarting your actors, but maybe that's not always what you want. Here is a nice graph, because I needed to have some graphs in this talk as well, so here are some bar charts. But these are from the article is called Analysis of Exception Handling Patterns in Java Projects, an Empirical Study. And first things, like this is a big sample of Java code, and what most people do when there's an exception, they log it out, okay? They say, hey, here is an exception. Good luck with, you know, fixing it. The second most common thing to do is sort of the dirty version of the log statement, is just printing out a stack trace. It's like saying, hey, here's a stack trace, good luck. You know, you might not even see it in the logs, or maybe you do. But these two alternatives are a lot better than the third one, which is still quite common. It's like the anti-block, which I believe is a way of telling the people operating the system, good luck, and screw you. So this is sad. This is the sad reality. I mean, if you're operating systems and you see this, this is not going to help you. And then there's a more civilized way of, you know, throwing something up the chain. Maybe that will work. System out println, and why on earth you would want to do that? Anyway, so I think what this shows us is that by default, developers don't like to think so much as to what to do when there's a failure. They just go like, oh, ah. And so Akka is sort of trying to make it explicit that you have to do something by at least crashing the actor. So when there is an exception thrown inside of an actor, what it does is it's crashing. Like, let it crash, that's the mantra of the Akka team. You sort of get this crash, and then the supervisor needs to decide what to do. Will it restart the actor? Will it stop it? Will it escalate the failure? Will it do something funky in between? We don't know, but there is a way to handle it. So as Joe Armstrong, who developed the Erlang programming language, put it, repeat after me, errors should be handled out of a band in a parallel process. They should not be a part of the main application. So what that means is that when you're writing your application code, you don't want to think about, you don't want to think about failure. You want to focus on when the happy path, when everything goes well. That's your business logic. You want to write this, you want to read this. And then if something bad happens, this is something that you handle out of band. And what happens in an actor system is this is going to be logic that lives in the supervisor. The supervisor is going to deal with this. It's going to be able to do things like using a back-off strategy supervisor, which says, I'm going to try and restart this actor in, after 2 seconds, after 4 seconds, after 8 seconds. So it's an exponential backup strategy that you could be using there. If you were accessing a third-party system that you knew sometimes just crashed, you don't want to sort of repeatedly try to connect to it, because that's not going to help you. So there is a lot of power and a lot of ways in which you can make your system a lot more stable by dealing with failure. But for this, you have to build hierarchies and do failure handling through that. So I hope that I made my intent clear here. If you use Akka, also use the failure handling part. Don't only rely on doing concurrent things with it. Also use this. Okay, third one. It's getting darker, isn't it? The mother of excess is not joy, but joylessness, by Friedrich Nietzsche. So this third anti-pattern is too many actor systems. Granted, I've only seen this once out in the wild, but this was once enough, so I sort of stepped back, brandishing a cross and moving away from it, because it's if you have this, it's bad. You're in a bad state. What I mean is this: you have one JVM, that's the red square, and inside of the JVM you have many actor systems. In this case, it was up to 140 actor systems in one JVM because they had 140 connections. And you know, the intent is good because it's about isolation. It's about isolating things. So they thought that by having separate actor systems, they were completely isolating things. It turns out that when you do this, you don't isolate things very much, and you don't really understand what Akka is doing. Akka, or each actor system, has a default thread pool attached to it. And thread pools are expensive. They cost memory, and they have threads. And if you have 140 of them, you will end up with a lot of threads. You're going to, you're going to sort of beat Tomcat in amount of threads that you have. And we all know that the execution model of Tomcat, which is based on one thread per request, is not so great when it comes to scaling. So that's not, that's not ideal. You're contending for the same resources on the machine. What to do instead? Keep calm and trust Akka. Akka is built around this idea. And again, it's our friend the dispatcher that's going to come and help us here. So the idea here is that we have bulkheads, like on a boat, like on the Titanic, except that on the Titanic, bulkheads were not closed. So the Titanic bulkheads, they would stop here and they were open up here. The idea of a bulkhead is you're being hit by an iceberg here. So these two guys have a hole and they can fill up, but the rest are not going to be filled up, and then the boat doesn't sink. Except for the Titanic, for whatever reason, they didn't close them up here because I don't know. I don't remember what the idea was, but then these two guys had holes, and then they ended up filling up the whole boat, and then it sank. So if bulkheads are done right, and if you're using separate dispatchers like here, you're going to be able to influence and limit how many threads are available to each part of your application. So for example, here we have, for example, say a graph database that has we know this graph database uses blocking calls. We don't want to have it hog too many threads at once, so we're limiting this. It has 2 threads at the most with a fixed thread pool here. And then we can use this when we define how to create the actor by defining the props. We can say, well, use this dispatcher, which means that when when this graph actor is going to be created, it's going to be able to use at most 2 threads. And so we are isolating this part of the hierarchy or the part of this Akka application from the rest, and that way we're safe again. Another thing we could do is say, I need at least 10 threads at all times for this part of my application, so you could enforce the same kind of thing here. All right, so use dispatchers. Next handy patterns, words, words, words. That's from William Shakespeare's Hamlet. Any idea what this is about? Sorry? Logging, yes, logging, perfect. Logging in the wrong way, obviously. So logging is something we like to do because it's useful when we develop to see what's going on. Running the debugger at all times is maybe, especially if it's a concurrent system, is not the nicest thing to do. So logging is useful, except that you can, and this is not only for Akka systems, but for systems in general, logging is probably the reason number 1 for poor performance in systems, because what you can do there, you can do a lot of things that just destroy your performance. So what you could do is string concatenation. You can say, I have a debug statement where I'm using this syntax here with plus. And maybe toString is calling the database. I've seen this. This happens. There's toString methods that call the database for whatever reason. And even if they don't call the database and concatenate many fields in a large object graph, they're still going to be costly. Even if this line is never going to be invoked, the fact that you have a plus here means that it's going to be run. So you don't want to do this. One other thing, the number 1 offender actually above this is non-asynchronous logging. Logging to a file and writing to it synchronously in a blocking way. This is completely killing your performance because suddenly whatever you do is tied to the performance of your disk, even though maybe you don't need the disk at all. Other things I've seen is not turning debug logging off in production settings. then you have a lot of logs, and maybe you didn't need them. And let's be real, because this is 2017. In 2017, we shouldn't be logging to a file on disk anymore. We should be sending things off to a centralized logging thing where we can see the logs of all of our systems in production. Logstash or other systems come to mind. So this is one thing I just wanted to pass across here is if you really want to monitor live systems, you probably want to log to a place that's available centrally, and we can search for logs and set up rules, etc., etc. So especially in the context of actors, this is bad when you get logging wrong, because actor systems are really meant to process like millions of messages per second. And if you get this wrong, you're completely destroying the performance of your actor system. And then you're like, oh, but Akka is slow. But Akka isn't slow. It's just your logging is slow. So how to build, how to go about this? Please use Akka's built-in logging facility. Don't invent your own or use another library. It actually uses asynchronous and asynchronous stream when you log using the built-in stuff. If you configure appenders, make sure you use the asynchronous variants for logging in files, etc. Use string interpolation. So that's very easy. You say received and then message and then this open-close curly braces, and here you pass whatever you wanted. So this is only going to be run if this is not going to evaluate as toString or anything unless it's really needed. And then, I mentioned Logstash and friends before that. Use that if you want to monitor your things. Right. Next one is my favorite one. All that we see or seem is but a dream within a dream. Very nice poem, Edgar Allan Poe. Any idea what this is about? It's subtle, but so it's going in the direction of being out of touch with the hardware. And what I mean with this is that. And that is the sad truth of, I think, 2016, 2017. And let me just rant here for maybe a bit under a minute. It's not because you use Kubernetes that you have a microservice-based platform. Using Kubernetes just means that you use Kubernetes, and now your life is a little bit sadder every day. And especially if you have an Akka application and you run maybe Kubernetes inside of a virtual machine, because, I don't know, that's how I've seen 2 out of 3 Kubernetes deployments in production, is that you first have a virtual machine, inside of this you have Kubernetes. Don't ask me why. And then you have containers, and in the containers you have a JVM, and inside of the JVM you have an Akka application. And then you have your Akka application, and I really like this quote by Martin Thompson here. Hardware tries so hard to make software fast, software tries so hard to make hardware slow. I think this really hits the point here. We have great hardware. 3 weeks ago I bought a desktop computer. It was the first time in 10 years. I now am the proud owner of a 4.2 gigahertz Intel Kaby Lake computer with, I have a SSD drive that's strapped onto the motherboard with 1.5 gigabyte write per second. I can compile, it's fast. When I go back to my laptop, I feel the pain of it being slow. So we really have great hardware. It's just like we at the same time we try to abstract everything away from the hardware. We try to put our code very far away from the hardware so that it has no chance of being fast. And if you're using Akka, what happens is, Akka sort of, when you configure it, when you use the default fork join executor, this is the default configuration here. So you have to give it the parallelism min, the parallelism factor, and the parallelism max. And the funny thing here is this value here. This actually is the ceiling of the available processors, the available CPU cores, times the factor. That means that somewhere in how Akka runs and ticks, it sort of needs to know a little bit about how many cores it has. Now imagine you're one of 140 Docker containers inside of a virtual machine, and maybe your machine has 16 cores. But then again, if you have 140 Docker containers or whatever you have running on the machine, you again are in this place where you're contending for the threads because you're spinning up virtual threads and you don't map them to real hardware threads. And really, Akka only shines when you have these things are fine-tuned and match. That's if you're interested in performance. Maybe you're not interested in performance, then or you can run whatever you like. But I would think that one reason for using Akka is because you want things to be fast and to perform. So another thing that's I mentioned most of these things. Another thing you're contending for is the network. If you have one network adapter, it's better be really fast if you want to stream out on many virtualized things and systems. So what to do instead? Know what hardware you actually have you're running on and configure it, fine-tune it in production. Make sure that if you're using virtualization, you know what's going on and make sure that the hypervisor or whatever thing you have is not lying to you. And if you run load tests, that's also something I've seen, load them on the same target architecture than the production target platform or hardware that you have. If you're running load tests on something that's not going to be exactly one-to-one the same hardware as the production environment, it's not. It's a load test, but it's a useless load test. It's not telling you anything that you need to know about your real system. Okay. Next one is going to be a little bit less inspired by the great minds of our human history, but still I would say that it's quite fitting in this context. Some men aren't looking for anything logical like money. They can't be bought, bullied, reasoned, or negotiated with. Some men just want to watch the world burn. And that was Alfred in the movie Batman, The Dark Knight. Our next anti-pattern is blocking. Blocking in an actor system, blocking when you're using actors, that's something, How can it happen? You could be calling a synchronous API, and that's probably the most common point where you're going to cause blocking instead of an actor is by calling a synchronous legacy API. You could also be explicitly waiting for the completion of a future using in Scala the await operator. It's like, I'm just going to call await here, nothing bad is going to happen. And then your system runs hot, you have many requests, and then this one place where you use the await is crashing the whole thing. Same thing, using thread sleep is also, it's like, I'm just going to call thread sleep here to get rid of this race condition that I have on my laptop, and I didn't really test if it's the same amount of waiting that I need when I'm running it in production, but what could possibly go wrong? Well, lots of things can go wrong. Don't block, really, don't block. It's a bad idea. It's always going to come back and haunt you, and you're going to wake up at 3 in the morning and have to fix this, and it's painful. So what to do instead of blocking? If you have a legacy API that is synchronous, just put it at least behind a dedicated dispatcher. You can also use, there's a syntax in Scala that you can use. It's actually called blocking. So you write blocking, open curly braces, and then in this blocking block, if I may, you put your code that is blocking. That's going to tell the fork join pool that this code is blocking, and it's going to be able to do something about it. If you use a dedicated dispatcher, you're limiting the damage. You're not allowing this one part of the code to take over the whole thread pool and sort of creep everywhere and slow down the whole application. If you're using futures, if you have asynchronous calls, use the pipe pattern. We're going to see how this works now. And if you need to wait for 2 seconds, don't sleep for 2 seconds, but use the Akka scheduler and call yourself back in 2 seconds. And if you're afraid that other messages are going to be in the mailbox while you were sleeping for 2 seconds, use a control-aware mailbox, one that makes a distinction between normal messages and control flow messages, because then you can sort of skip the line and have this message be processed first. Ask and pipe. So this is an example of using these two patterns. I have here a thing that receives a message, compute pi. So I want to compute pi to a certain precision. And I'm going to delegate this computation to the pi actor. And I'm asking the pi actor to compute at a certain precision. I'm also passing in who wanted this, the original sender. I've captured this here. And this is going to be bound by a timeout of 5 seconds. And then in this result here is going to be a future of pi. And I'm going to recover this. So this is a future. I'm recovering the case of an ask timeout exception, something that's thrown after 5 seconds if it didn't complete. And then I can wrap the result here. I can transform this into a computation timeout. So I have this result, which still is a future, and I'm piping this future to myself. So this is a simple example. I'm piping to myself. I'm sending a message to myself. I could be sending a message to someone else. Here I'm just sending a message to myself. And what that means is that I also need to cater for 2 more messages coming in pi. If everything went well, I get the value of pi that was computed. I can send this back to the original sender. Or I have a computation timeout, the one that I created here. I can also send this back to the original sender with an error message. So of course this is a simplified example, but you get the idea. Here the idea here is you have a future here, and as soon as it completes, the result is going to be sent to myself, or to another actor for that matter. So I'm transforming an asynchronous computation into a message being sent. And that way I'm sort of integrating again asynchronous computation, or a future in this case, in my message passing paradigm, the one that I'm using when I'm working with Akka. Okay? Right, next. A man who dares to waste 1 hour of time has not discovered the value of life. Charles Darwin. And here's a fun fact about that I only learned about 2 weeks ago. I started reading a book called Rest, which I highly recommend. Charles Darwin, do you know how many hours per day Charles Darwin was working? How many? 4, yes, 4. 4 hours. And I think this has been lost, so our brains apparently aren't very good at working 80 hours per week. So all of our culture of, working, burning the midnight, just working 60, 80 hours plus per week, this is not very good if you were in a creative work. So you're much better off if you're working a few hours, 4 or 5 hours of really concentrated work per day, and then do some concentrated rest per day. I think it's not so easy to actually live this in practice. Maybe if you're completely able to steer your own time, you can, but it's increasingly harder, especially where environments where everyone is supposed to be online on Slack all the time and receive messages and so on. But who knows? So I just wanted to mention this because I think we're working crazy hours, and maybe not all of us, but I think probably going back to doing things in a little more, something that's better for our brains is maybe going to help us do better work. Who knows? So that being said, our 7th anti-pattern is reinventing Akka tools, because this is really what this is about. It's about wasting time. And how can this happen? Well, you could not have read the whole documentation, and I wouldn't blame you, because the whole documentation is pretty long. It's very nice, but it's also very long. And the other thing you could be doing is also not being able to keep up with updates. There's a lot of work going on in the Akka space, a lot of new things, so you could be missing that now there's a feature that you need, and sort of be tempted to invent it and write it yourself. So I'm guilty as charged here. I've done this. What you could be reinventing, well, at least once delivery. If you want to make sure that a message will be delivered over the network, at least once. You cannot ensure that it's going to be delivered exactly once, but at least once will do. This is already there with Akka persistence and the at least once delivery trait. You have this out of the box. Backup supervision. I've talked about this before. If you have an actor, for example, that talks to, say, a database or a third-party system, and it crashes, then you don't want to hammer it every millisecond or every few milliseconds and ask, are you alive, are you alive? You want to use exponential backoff and come back to it at increasing intervals of time to not overflow it. Message prioritization, I've also seen this. You have an actor and then you have a queue in the actor. You don't need this. We have mailboxes. Mailboxes are there for this. I mentioned the control-aware mailbox. This is just a message where you have a marker trait where you can flag some messages and they're going to skip the queue. You have a priority mailbox. You have a stable priority mailbox. Use these things and don't reinvent them. Why this is bad is, well, you need first the time to write it, and then you need to maintain what you've written. And I think the time necessary for maintaining code that you write on your own is, over the lifetime of a system, is something very often underestimated. You end up with code that would not have needed to be there, so that's always a thing I tend to try to avoid. You know what to do instead: read the documentation, or call me. Please don't call me at night. I live in Europe. Don't call me, So, yeah. Next anti-pattern, and I think that's already the last one, so that means we're going to have some time for discussion and questions. This is the way the world ends. Not with a bang, but with a whimper. And our last anti-pattern here is using Java serialization. And you will notice the nice scenery and the nice pictures here, and the four writers of anyway. So why is what do you need to do in order to use Java serialization? And here's the bad thing: nothing at all. It's the default. Okay, so if you use Akka and you don't do anything, by default your serialization is going to be the Java-based one, and this is bad for several reasons. It's happening in several places. So one of the places is if you use Akka persistence. If you use you have a journal, and the messages that are written to the journal are going to be serialized in binary format using Java serialization. And the other place is when you send things across the wire in a cluster. That's also Java serialization, or whatever serialization you've configured by default. And this is bad because, well, first off, the performance of Java serialization isn't that great compared to other things. And especially if you're writing something that runs in a cluster and you want to sort of do a rolling upgrade, if you have Java serialization, and if an old node gets something new, it's going to blow up, or depending on, of course, of the semantic changes, etc. But Java serialization isn't meant for this. There's other formats, such as protobuf, that are a much better fit for this. And then in terms of persistence, it's the same thing. Imagine you have a persistent journal or a snapshot store, and the thing crashes, and it tries to recover, and then it cannot deserialize something that was persisted. That's also a bad thing there. So please don't use Java serialization, or don't use the default, but do configure something appropriate, such as protobuf, Avro, or thrift. Avro is an interesting one. So unlike protobuf, which is has a per field approach, Avro has a schema approach. There is a schema registry for Avro schemas for Kafka, where schemas are being stored with Kafka and sort of distributed in a system using Kafka. And this is a pretty interesting one. So you describe the whole schema, and you describe a way to sort of, you need a schema and data in order to sort of deserialize the thing. And this way you can evolve systems, especially distributed systems, where potentially many people are involved with writing a system. This approach I find to be quite interesting. As opposed to using a flat format, or don't use JSON either. I would say even if you can read it, you then lose a lot of performance over that. Yeah, and that's pretty much it. So I think since we have a bit of time left, are there any questions?